Hi, good evening. So we'll start it now. Hello. Hello. Students, am I audible?
Yes, I audible.
Is it visible that slide week 5? Is it visible? Can you read out what is there on my screen?
Shortest person method graph.
Fine. Great. Okay. Yeah, we'll start now. So because already it's 8:04. Look at now. Actually, as I already discussed, that week number 4 is exclusively the BFS and DFS also. But there it is. See, zoom reduce. Yeah. So when you will recall that BFS or DFS, whatever it might be, then whether it's breadth first search or it might be that depth first search, we are finding that graph in terms of levels and shortest path is in terms of number of edges. Like you want to travel from 0 to 5. So we are counting that number of edges like 1, 2, 3. So that is what is happening in the BFS. Actually, it is like would be DFS or BFS. So whether that particular edge is reachable or not, sorry, that particular vertex is reachable or not, we are trying to find out it. So from 0 to 5, do you have a path for that? From 0 to 6, you have a particular path is available or not. So that is all about that the week number 4. So from the week number 5, so one more property is added for that graphs, that is called some weight. Some number is added. So this number is exclusively added for the edges. So the edge it is 0 to 2 we have 80, and 1 to 2 we have a 6, and 0 to 1 we have a 10, something like that. So this we can consider that it could be a cost, it could be a time, it could be a distance. Someone says, you want to travel from one city to another city. So what is the fare? What is the ticket price for that? That could be a cost. So how much time you require to travel from a city A to city B? Then what is the distance between them? So something like that. So this is a graph. So what do you say that graph is nothing but a collection of vertices and collection of edges is there. Make sure that. So a weight is nothing but it is having some kind of reasonable weight. It could be a number, some edges, every edge is assigned with some kind of weight. It could be, let us be consider it could be a positive number right now. So at this instance, we consider it's a positive integer. So how you will represent the adjacency matrix for this? Because it's a weighted graph. You have weights are assigned, 80 is assigned, 6 is assigned, 70 is assigned. How do you store this value in terms of that data structure? It could be that adjacency matrix. So you already learned this name, adjacency matrices. So it's combination of rows and columns, where the rows and columns are labeled with the vertices which are there, like 0, 1, 2, 3, 4, 5, 6, something like that. Rows and columns are same. How many number of vertices is there? Similar kind of thing. But here you can find it whenever there is a path. So like 0 to 0, so we don't have path. So absolutely we don't have path means definitely you have the representation of 0. 0 means no path. 1 means there is a path. Along with this 0 and 1, like true and false. If true is there, it's 1. Like a path is there. If the edge is available, you are representing with 1. If no edge is available, you are representing with 0. So along with this, there is one more is added. That is called weight. So this weight, when it is having greater than 0, so definitely there is a path is there. Along with this, there is a weight is available. Like 0 to 1, we have a path that is 1, and what is the weight is associated with it? It's 10, something like that. So similar way, if you can find it that 5 to 4. So you have a 5 to 4 is there. So whenever 5 to 4 is there, you have that path is available, so that it's a true. So what is that? Wait a minute. It is 5 to 4. So yeah,
Excuse me,
it
sir.
is 5 to 4. Yeah, tell me. Hello.
Sorry, sir. Sorry for interrupting.
Hmm.
Uh, I have one means This is week 5 class. Meant you were saying that there was something revision class that is different or this thing.
Revision class is tomorrow, no? It is
Okay,
week
so
5 is actually the live session, which is open session. Whatever you learned in video,
yes, sir.
that I'll do a quick review.
Okay, sir. Okay, sir. Thank you, sir.
Okay then.
Thank you, sir.
So it's not like quiz one revision session. I think quiz one revision schedule is scheduled tomorrow. I think so. Just you can find in calendar.
Okay,
Okay,
sir. Thank you, sir. Thank you,
fine.
sir.
Yeah, so there is a weight is associated with it. That's a 50, so that it is a path is available. 50 is available. So similar way, if you go for the adjacency list is there. Same thing. When is the compact format? What do you say that adjacency matrix is a more detailed format and it requires that a space, a large space of memory is required. Whenever you come to that adjacency list, which is a compact format, like so the zero vertex is associated with 1 and 2. So and it is having weights that 0 to 1 is 10 and 0 to 2 is 80. So similar way, the fourth vertex, vertex 4, which is available associated with 1, 5 and 6, and it is having that respective weights. So whereas 20, 50 and 5. So this is essentialist. The record is along with the weights. So not only the simple vertex which is connected, the vertex 4 is connected to 1, vertex 4 is connected to 5, vertex 4 is connected to 6, along with associated weights of 20, 50 and 6, which is compactable and which is easy format to store it so that space can be reduced. Time complexity we don't consider. Whenever you are representing different kind of streams, like you have adjacency matrix is there, adjacency list is there. Adjacency list is somewhat compact format comparatively adjacency matrix. So I'm going for 8th slide. Shall I move it? Any clarification about weighted graph representation in adjacency matrix and adjacency list? Any clarification? Shall I go for 8th slide? So maybe next slide is 8th, I think so. Hello? Shall I proceed then?
Yes, sir.
Ah, so this is a representation, how weighted graph is represented in terms of adjacency matrix and adjacency of list. So you have that, yeah, shortest path, because some of them are repeating, so that wherever it is combined and closed slide is there. So there I'll stop. Yeah, here it is combined and closed. See, look at it. So what exactly here is, so the weighted graph adding up, we are doing the adding up of it. So what we are adding it along with the path, it is traversing from 0 to 5, something like that. Along with the traversing, we are trying to add that whatever weights are associated with. So the weighted shortest path need not have that minimum number of edges. We don't consider that how many number of edges are required to travel from 0 to 5. Like, so to travel from 0 to 5, so we have 1, 2, 3. So 3 edges we are using for traversing. We don't consider that. We consider that weights are associated with it, like 10, 30, and 50. So total weight is going to be that 80. This is going to be considered. We don't consider that number of edges. So please remember it. So let's go shortest path from 0 to 2 is via 1. Like, so they are considering not like number of edges. They are considering in terms of 0 to 2. So please see that 0 to 2, we have two ways. Like we can go 0 to 1 and 1 to 2 is the first path. And we have a direct path is available 0 to directly to. But whenever you go to the 0 to 2, it's going to be the 16 is the total distance. We can say that. So whenever 0 to 2, it is going to be the cost around that 80. So that we don't consider this one. We consider this path only. Even that number of edges is the 2. So I hope you got it. Shall I go for it? Next one. We don't consider that number of edges. We consider that weights. The summation of the weights, how much it's required to travel from one vertex to another vertex. Does it okay? Shall I go for next?
Yes, sir.
Fine. So we are going for the next. 18, 10. Yeah. So 9th and 10th is it is having almost similar. Only adding of right side is added. So wherever the animation is ended, there I'll, yeah. 10th one is okay. See, we find that the shortest path, whenever weights are associated, so there are major two categories of it. So one is that single source shortest one, and next one is all pair shortest one. So let's we focus at least 2-3 next kind of sessions, or session in the sense next kind of slides, lectures, which is completely single source shortest, but then we'll work it about all pair shortest one. So first we focus on that single source shortest. You know, single source shortest is very simple. From a fixed vertex, we have to fix one vertex. Like if you consider the previous graph, you fix that you want to traverse from 0, you fix it, or you want to traverse from fifth vertex, you fix it. From that, you want to traverse for all other vertices. This is called single source. The transport finished, like this example, the transport company is available, so which is having a product from the factory. You will receive one product, a collection of products is there, which is received from one particular store. It might be the store, what do you say that? From here you need to distribute this one to different retail outlets. You are the different retail outlets are there. This is a central store, what do you say that? From the production we got that central store, from that we have to distribute it. So for that distribution, we are trying to find out the shortest path in terms of the distance or in terms of cost. Please remember, because weights are associated. And similar way, you might have a different path, So you have the path something like this. So you might have the path something like this. So we are choosing whichever the optimized one. Even you might have that from central path to this one also. It's not issue there. So similarly, the courier company is there. So they want to deliver that items from a single source. It is also same. So you have the courier company. So almost we got 15 couriers, 15 letters it might be. Letters we consider, or 15 parcels are there. We want to distribute to different places or different addresses. We always choose that. So different kind of ways, which is going to optimize the distance. Like he will travel from A to B. After going from B to, he may not go for C, he directly goes to D, because there might be a shorter distance is there. From the D again we have a shorter distance to E. From the E has a shorter distance to C. So definitely he chooses. It's easy. He doesn't choose it something like A to B and B to C and C to D, because of the weights or distance. So between the vertices, what is the distance is available, this weight, it makes a difference between a source to a destination. So this is the weight is going to be considered. So which is the shortest weight is stored. So that way, shortest one is chosen. But remember, it is considered as a single source. Always we consider the distance from central store to all other vertices. It's not like between this vertex to this vertex. We consider the single source. So whenever multiple, like all pair shortest path is there, that time we'll discuss some more examples is there. There is some complete kind of algorithm and complete kind of example is there. We'll discuss at that time. At this moment, few of the upcoming lectures, which is about that single source shortest one only. So we'll focus on it. Okay. So I'm going for the next one. Yeah.
Sir, multiples.
Yeah. Tell me.
That the all pair shortest path is that the difference between single source and all.
Multiple one is finding the shortest path in every pair. Like so we are like you are starting from 0, 1, 2, 3, 4. So like you have something like here the weight 1 is available, weight 2 is available. So in this case, what do you do that you are starting from this place, we try to check this weight, Like 0 to 3, how much weight is there? From 3 to 2, we are choosing. From 3 to this one, you are choosing. Here, we always consider the cumulative sum. Here it is 0 is started. From here, some 7 is added. See, look at. If you consider this graph only, we always started from 0. For example, we started from 0 to 1. So 0 is started and 1 is ended. From this one, we are choosing which is the shortest. From here to 4 is shortest, or from 1 to 2 is shortest. So we choose the 6th one. But whenever you do the distance, how much distance, you say that 10 plus 6. We don't say this 6 part exclusive one, because always we consider how much distance is taken from single source. But whenever you think about multiple sources there, all vertices, what do you say that, from this one we choose it. Let us we consider this one is there. From this 5. From this 5, we have 2 paths is there. 5 to 4 is there, 5 to 10 is there, where it is not a single source. It is some other source. After reaching 5, you decide. After reaching 6, you decide. We don't consider again cumulative sum, like 10 plus 20 plus 50 is not considered. That is the next examples we'll understand. Like after 2 lectures, you will have some more examples is there. We have multiple sources there. Upcoming 2 lectures is exclusively single source. Always distance is calculated from single source. We do the cumulative. We do the cumulative sum from 0 to 5. You say that 10 plus 20 plus 50, total is 80. Clear? Is it clear? Multiple sources not considered. Right now, we'll discuss later this example better. Okay. Hello. Hello.
Okay, sir. Okay, sir.
Even you can take a real example. See here, there is a real example is given. So optimal airline is given. Railway reservation is given. Road routes is given. So whenever road route is there between cities, so you consider that like A to Z you want to traverse. So between that you have C is there, D is there, L is there. See, look at, you have a direct path is there. We have indirect paths also there going to Z. So if you direct path is there, which is 80 is there. So indirect path is there, like 7 to 9 is there. What do? You select that even it is a long distance, even in terms of number of edges, like 1, 2, 3 edges is there. Even 3 edges is there. We select the optimal route in terms of fare or distance. So at that time, like you have another path is there from D to L is there. Again L to Z is there. So every time, once you reach a one vertex, Vn, from that vertex Vn, you choose it, shortest path. We don't choose from the beginning source. Beginning source always we forget. That's a tendency of that all pair shortest. Always we forget that beginning source. We don't remember it. We try to find out the shortest path from every I and J. We try to find out Z to C. We try to find out D to A. D to A, you have 2 paths is there. So like D to C and A, D to Z and A. So in that way we choose it. Every source is changed immediately. So I can tell you that updates have happened for every cycle. I'll show you that. One example is there. A fantastic example Prof had given. So in that example, you will understand better. In every cycle, the updating of weights are changed. Okay. So we'll understand after coming up 2 lectures is over on single source. We'll understand better on that multiple sources. Okay. Shall I go for the next? Hello.
Yes, sir. Yes.
Hello. Yeah. So let us we consider that negative and non-negative edge weights. Actually, weight can be always positive. Sometimes there might be a situation negative edges are there. So some kind of cases are there. There is a particular instance or real-time scenario is considered. So sometimes the negative weights also meaningful. Like, there is a taxi driver. So all of his daily routine is finished. Like he completed his complete calls of that uh, traveling to different customers. He has been traveled. At the end of the day, he's traveling towards home. he's traveling towards home. So when he's traveling towards home, so his car is going to be empty, but it consumes fuel. Definitely it consumes fuel. So during his travel, few customers are available, but he is driving that is empty with like, because he wants to make it directly going to the home. So if you pick up one customer, maybe his destination is different. So at that time it's difficult. So at this time, even it is a negative expenditure in terms of fuel consumption. Am I right? Fuel consumption. But it results, it's a positive weight. Even you represent the negative weight there, no issue. It doesn't create any problem because we are ultimately going to the home. Some fuel you have to consume it, no problem. But if the same road as having many customers, few customers is not a problem. Whenever many customers is there, at that time what happens, you might get that more profit. More profit means definitely your negative weight is a problem. Negative weight. So at this time, the negative weight is going to be increased because you are traveling to the home. In a busy road, you are traveling. In the busy road, you might have a chance of many customers. You get a chance of it, but you are traveling without picking up any of the customer. Due to that, you will get a loss for that. So at that time, also you will get that negative weight. That negative weight is going to be higher comparatively the negative weight in terms of fuel consumption with few customers. So I hope you got this particular instance. Okay. Hello. I hope you got that instance, this example. Any problem on this understanding? Both of them negative, but in the second scenario, many customers is there, negative weight is more. In the first scenario, few customers are there, negative weight is less. So in this negative weight is less means indirectly we can say it's a positive weight. Clear? Even it is represented with negative. Fine. So now the issue is negative weights are different, negative cycles are different. Repeating a cycle with a negative weight, it results again negative only. See, the negative cycle is one whose weight is negative. Some of the weights of the edges that will make up the cycle. Even if you make it that A to B and C, so you have negative cycle is formed. Negative cycle, there might be D's available. So you are having that 2 and 1 and -7 -3. So keep on doing the cycle, every time you get that negative weights. So this cycle is resulting negative weights are increasing. Negative weights are increasing. When that even you go that any kind of cycle, you go that A to B and B to C and D again keep going, never been reduced, and negative weights are keep on increasing. So when it is increasing, some of the weights of the edges that make up the cycle, by repeatedly traversing a negative cycle, total cost keeps decreasing. So that means simply the negative cost is increasing. What exactly it is? Keep on repeating in the same cycle, your negative cycle is keep on increasing, so that definitely your total cost is going to be decreased. So if a graph has a negative cycle, shortest path is not defined. So you can have negative weights, but negative cycles is there means shortest path cannot be defined. So without negative cycles, we can compute the shortest path. Even some weights are negative. Understood? Negative weights can be there, but negative cycles are not allowed whenever you are doing it is shortest path algorithm. Is it clear? Single source shortest?
So
Okay.
can you explain negative cycle again?
Negative cycle is you are going for A to B and B to C. You might have another cycle D, again from C to D, and this A to D is there. So you are trying to reduce that. Sorry, it's not directed because we are not considering right now direct. Yes. See, look at. We are going at us 2, 1, -7, and -3 is there. So with single source shortest, we are going from A to D, we are going. So whenever A to D, we are going, it is 0, 2 and 1, 3 and -3, it becomes 0. So 0, 8 is not meaningless. So we go in this way, A to D, -7. So -7 is not profitable. We keep on repeating wherever it's possible. Like 2, 1, it's 3 and 0, -7. Never been it is increasing my particular profit. It's not going for -7 to, if it is going for -7 to -3, it's fine. Is it right or wrong? Okay. If cycle is repeated, it is reducing that negative weights. So then it's no problem. The cycles is not a problem. But cycles, when the negative cycle is there, keep on subtracting from negative to negative. What happens? That keep on increasing the negatives only. So increasing the negative means what happened? Your positive values are decreased. So your total cost is decreasing means, so a shortest path is not possible. We can have negative weights. Negative weight minus positive. Like if you have 7 minus 2 is okay, no problem. Fine. Is it okay? Because you get the result is positive. Fine. Sorry. It is 5, no? I'm sorry. It's a 5. It's a 5. But whenever you have that -7 and -2, it results what? It results what? Hello?
-9.
Yes, -9. So it's keep on increasing. Negative cycles, what happens? Keep on increasing means your particular total cost of profit is reduced. When the profit is reduced, negative cycles are not encouraged. Negative weights might be there with combination of positive weights. Your shortest path can be measured. But negative cycles, keep on repeating negative cycles is not possible the shortest path. We cannot compute shortest path. Clear? Hello? Is it clear? Because shortest path is addition of weights, no? Weight 1 plus weight 2, no? Is it right? Is it right?
Yes.
Yes, sir.
So that whenever positive value is higher and negative value is less, if you do it, no problem. That is 7 and -2. So no problem. -5 you are getting, no problem. Whenever keep on doing something like negative and negative, it is increasing negative so that profit is reduced. You don't have a getting of chance of positive numbers. When positive numbers, you're not reducing that negative cycle. So that negative cycles are not advised. See, computing the shortest path in negative cycles is not possible. But without negative cycles, having negative edges is no problem. 1 or 2 negative edges is there means no problem. Fine. Clear? Okay. Shall I go for next? Hello?
Okay, sir.
Yes, sir. Yes, sir. I think generally we don't need for a confirmation. We can continue to proceed.
Yeah.
Only when we have a doubt, we'll stop you.
Cycle is that A to B, B to C, again C to A is a cycle. So this cycle, if it is resulting in negative cumulative sum, so that is not possible for shortest path. If it is not resulting negative, then no problem. You can proceed with the shortest path. Clear? Yeah, this is the same summary, whatever earlier it discussed. So that is different single source is there, all pairs shortest is there. All pairs shortest we'll discuss in the next. But single source is that upcoming 2 lectures is completely single source. Okay. So we'll go for that 5.2. Yeah. So now that actual details of single source is started. So let us we consider this one. So this is single source shortest one. So almost some slides are equal. Wherever the animation ends, there I'll stop it. So it is 5.2. Yes, here it is okay. Yeah. See, look at it. So this is the graph is taken. This name itself, it is telling, please understand, we start from a single source. We fix one source. From that, we keep on traversing. So right now, we already fixed one particular source is 0. You can decide whether you start from 6, you can start from 3, you can start from 2. But right now, for this example, they have taken from 0. Even this algorithm, you can apply from any source, whatever source you like it. So here, from 0 to all other vertices, you have to keep travel. From 0 to 2, you have to cover, 0 to 4, you have to cover, 0 to 3, we have to cover, 0 to 6, 0 to 5. From 0, you must be able to visit all of its, any of other vertices in the graph. That is called single source, all other vertices. So imagine, I think they consider in terms of that oil depots is there. So they are setting a fire at 0th one, which is the starting vertex, starting vertex or origin. So the fire travels in the uniform speed because all of them will burn in a sequence of it with equal speed. You know, in this speed, like 0 to 1 is not higher speed, 0 to 2 is not lower speed. All of them are same speed. This 80 is considered in terms of distance of the pipeline. Let us you consider this is a pipeline. 8 is the length of the pipeline, 10 is the length of the pipeline, 6 is the length of the pipeline, because it might be a cost or weight. For this scenario, this weight is going to be a distance. Let us we consider a distance. First, oil depot 0 or catch the fire 0 and the next vertex is once 0 has been fired without known time, you know, there is no waiting time is there, definitely immediately it is fired, so that the cumulative weight or distance is 0 itself. From this 0, you can start the firing from 0 to 2, it can start the firing from 0 to 1, but the distance is very low. It will complete that 0 to 1 first, because it's a distance is only 10. So by this time, so we get that weight is 10, because it is 0 plus 10 is 10. I think it's clear. So then after it, at this particular distance, only 10 of the 80 is finished. Still 70 is there. So then what happens, you know, 0 is finished, 1 is finished. The 2 can be fired through this 0 to 2, but the distance is very high. But meanwhile, you get the distance, very short distance from 1 to 2, that is 6. So that it is fired and its distance is updated with 16, because 0 to 10 and then it is 16. From 0, it is started within 16, like, you know, 16 weight, it can finish the 2 also. From the 2, before reaching 3, from 10, so from this 1, it can reach 4. So what happens, you know, here already 10 is there. From this 10, 4 to reach it, how much it is required is weight of 30. So that 4 is finished. By this time, still you cannot finish the third vertex, because it 0, 10 and 30. So keep on moving. You can finish up the 6 also, because it is shortest one. So 6 is finished means here it is 36. Clear? So sorry, it is 35. I'm sorry. Yeah, it is distance is 35. It is 35. And from this 35, you can quickly reach that 5 before it reaches that 7, 16 to, that is 2 to 6. You can reach 35 to 45. Sorry, 5 with a distance of 45. Then after it, and the last one is from the second vertex to third vertex, after 70 pipelines or 70 distance of pipeline is covered, it reaches to that the total cumulative of 86. So it is total shortest path from reaching from one vertex to another from a single source vertex. If somebody asks that how much distance from 0 to 4 means, you can say it is 30. 0 to 4 is 30. Somebody asks that 0 to 3, how much distance is that? 86. Somebody asked that 0 to 6, how much distance is? 35. I hope you got it. Single source one. Is it clear? The slide number 10.
Yes, sir.
So now we are going for that. Yeah, it is cumulative one. Yeah, same thing. What I solved it is same thing. It is showing in terms of like, orange color bubbles. Please remember here the time, how much time it's required. As and when firing is started, without no time of waiting, that 0th vertex is fired. It's a burn. It's burned. And keep moving immediately. So first vertex is burned, but this distance is added. The pipeline distance is added. It's a 10. And same thing is reflected to all. You can find it. Yeah, all vertex has been fired. Yeah, by this time all of them are fired. So you can look at from 0 to 5, it is 45 total time of travel, or from 0 to 3 is total time of travel is 86. From 0 to 4 total time of travel is 30. So this is simple, which I explained you in that earlier. Same thing is carried here. It is. And then we go for, yeah, it is again they are showing. Yeah, so how really it is happening, please look at here. There is a one particular approach is used. They are using infinite. So initially some value should be there. Expected burn time is required before you start any kind of vertex burning. So you required its initial value because it is a list as per your data structure. In this list, some value should be there for each vertex, because already you said, it is adjacency list and adjacency matrix is there along with the edge. So that particular vertex, you can find that weight of that, how much weight is associated with it. So initial value, what value you give it. So we are giving initially the infinite one. Initially all of them we are setting with infinite. See, look at all of them are infinite. So each time a new vertex burns, it updates that expected time with its neighbors. So whenever it's a burning, expected time is done, immediately it is changing it. So here infinite is changed to 0. Please listen, because initially it should have some value. That is what adjacency list or adjacency matrix we maintain. So whenever expected time, see, look at after this one, from 0, you have two expected times. Expected time for 2 is 80, expected time for 1 is 10. So that these two are resetted. Two infinitives are gone. Here earlier it was infinite. Here it is infinite is there. But these two are gone, because from 0, you have two descendants are there. Two adjacent vertices are there. That is 1 and 2. But of course, out of these two, we choose that nearest one. Nearest one is 1. That's what the next they are showing you. See, yeah. Two of them expected burning time is updated, but one of them only burned because it is the shortest. It is shortest. From here, you can see that. Next expected times is there. Please see that next expected time. If this is burn, then expected time here can be updated. But this is not at burn. So that next expected time is updated for this one is 30. But what happens, out of this 30 and 16, 16 is selected. The vertex 2 is selected. And after this one, after this 4, you can see that next expected time. So this is already burned. So that next expected time is this one, ET, expected burn time. From this 4, next expected burn time is there, that is 80. See that 86 is over. Yeah, after 4 is burned. Yeah, it is 35. It is 80. So whenever one vertex is burned, immediately next vertex expected time of burn is updated. by overwriting infinite. Clear? Is it clear? Hello? Is it clear? Hello?
Yes, sir. Yes, sir.
Is it clear then? So
Yes.
whenever that expected time, whenever the particular vertex is burned, whatever adjacent elements are adjacent vertices are linked to it, their expected time is updated by removing infinite. Initially, infinite is very simple. That is already shown in the code. Anyway, when we'll explain the code, then you can understand the infinite how to calculate is the maximum weight is taken, and then they are multiplying with number of vertices. That's very simple. So here, so the same of them is carried up to, yeah, until all the vertices is burned. Yeah, here it is. Yeah, here it is. The algorithm is due is that Diksha's algorithm. This is the other who have been implemented this algorithm. The proof of correctness they are giving. So please look at the proof of correctness, how really it is correct or not. So please look at that. Diksha's algorithm. Yeah, it is carried for. Yeah. Yeah, up to here it's fine, because after that again new slide is started. Look at each new shortest path we discover extend the earlier one. Please remember, we extend the earlier. So you have a pool of that already burned vertices. So you have another two vertices is there which has to be burned. We discover it from the X. We are discovering one new path to the earlier one. So earlier one is X is there, earlier one Y is there. By induction, assume that we found the shortest path to all vertices which is already burned. Remember, so you next vertex to burn is V, that could be via X. And next vertex to be burned, that is W, via Y actually we are burning. But you might have one particular path, shortest path might be there. Like you have a shortest path. So like you have a 2 here, you have 3 here, you have 4 here. From the X, when you're burning V, okay, sorry, we'll change the values because via W we are not having any shortest. We'll change some other values. Here 2 and 1. Listen, the burn time of the W greater than the burn time of the V, so that's okay. Cannot find the shortest path. Y to V. Y to V means this is like Y to W, that is 2, and W to V, it is the weight of the total is 3, because it is 2 plus 1. But through X we already burned, because X is not linked to the W, so that it directly find out that X to V only, even the distance is 4, because W is not adjacent. So edge from W to V has the weight more than 0. So the argument breaks that if edge WV can have a negative weights, if the negative weights are involved, the Diksha's algorithm, negative edge cycles cannot be taken, only the positive edges only. Don't the limitation of the Diksha's algorithm is we cannot have that negative weights, only the positive weights have been taken. Clear? So that even because it is already greedy approach. Greedy means once X is burned, from the X it chooses that all adjacent. Once Y is burned, from the Y it chooses all the adjacent. Even you have a shortest path from Y to Y to W and W to V, it doesn't choose it because it's a greedy approach. Diksha's is using the greedy approach. So that's the reason it will approach this one. V is burned through X only, even it is having that 4 weight. Clear? And one more is, please identify that you cannot have that negative edge weights in the Diksha's algorithm. You don't consider it is negative cycles. Even negative edges are also there. It doesn't consider that Diksha's algorithm. That's a one limitation of the Diksha's. Okay. So I'm going for the next. Is it okay? Here it is a complete implementation. See, the implementation is, yes, So the complete implementation is here. So here you can find it is first basically the numpy array is taken. Numpy array, what it will do is you can have that array of multiple dimensions. Multiple dimensions, why it is multiple dimensions is rows is there, columns is there, and x also there. Please remember, so the x is nothing but third dimension which it contains the weights. So how the infinitive value is calculated, I'll show you that. There is a code samples was given. Even you can open your earlier here it is weight. I'm using 561 is the weight. Why it is 561 is very simple. Please look at here. 81 is there, no, the maximum one. Wait, our graph is available. The maximum weight is there. The maximum weight is taken. So our graph is there. Maximum weight is there. Look at the maximum weight. Yes. So maximum weight 80 was taken. So that's what it's taken in the 80. The max of weight. See, look at here. Yes. So maximum weight of the matrix is taken and multiply with number of rows. The number of rows is nothing but the number of vertices are available plus 1. So that it's resulting that 561 is the initial infinite value which is set for all of the vertices as expected burn time. You know, expected burn time is that ET. What do you consider, you know, ET. Expected burn time is initially 561. So before it is getting a chance for that expected burn time, initially it all sets to that 561. So after that, it is setting for all of them as infinite, and widgeted is going to be false. So that is what exactly it is happening. And then distance is initially as and when you started from a source vertex, because you start from a source vertex. Already I said it is a single source one. A single source one. A single source means you might pass it that 0th vertex. When you pass the 0th vertex, the 0th vertex initial time of the burn, you know, consider it is 0, because as and when it is started, it's going to be fixed that it is burned within no time of waiting. So that T is going to be 0, which already you know that in the previous explanation. After that, it starts at every time what it will do is minimum distance it will find out to all adjacent vertices. So the minimum time, minimum distance of it, like, you know, from the 0, it tries to find out the minimum. That is considered as that next distance to visit. From this next distance, if that is not visited and distance of V is it equal to the next distance, immediately the next distance V is created, a list comprehension is created. What do you call it? It's created as a list comprehension. So after that, next visited list is there. In that, minimum one is selected. Like you 0 to, you might have the multiple paths is there which it can visit. In this, minimum one is selected. Which of them is minimum? Like 0 to 1 is there, 0 to 5 is there, 0 to 6 is there. Which one is the minimum is there? That minimum is selected. Once that minimum is selected, visited is going to be true for that, and then it will mark it that that particular vertex is visited as a marker, like whether it is visited is a 1 and whether it is equal to 1, and not visited of it, and then immediately two of them, whether it is current distance is minimum or next visiting vertex, and then that particular adjacency matrix visited, which of them is minimum one, that distance is going to be find out it. So overall what happens, you know, it will recompute every time. It will recompute the distance of V. This recomputing is done for every neighbor of the V. Whatever you are visiting it, that every neighbor is going to be calculated as the next visited. In that every neighbor, we choose the minimum one. That's what in the every neighbor, we choose the minimum one. That is what minimum distance. Like the minimum of two parameters. The first parameter is current distance minimum, and next one is next visiting distance, weighted matrix of that particular, that intensity matrix of that particular next visiting one, and whether you have that already visited. Make sure it is visited. Out of it, whatever visited and the current one, both of them are added. Current distance and weighted one, and in that we are finding out the minimum. This is what the recomputing procedure, how really it is happening, and it is getting you that. Make sure the complexity is, it is overall n square complexity. The reason is simple. Here it is, you look at, this is overall complexity. So you have a outer loop. The outer loop is available. N times it is repeating. Clear? And we have an inner loop is available. This is for updating each minimum distance. So outer loop is making you that all of the vertices has been traversed, all of the vertices has been burned. As and when a vertices has been reached, whatever adjacent vertices are there, in that minimum distance is selected. So that two nested loops are involved. Here it is inner loop is involved, and here it is outer loop is involved. So both of them, it is making the complexities that n square. And of course, earlier complexities are there. When you are generating that infinite, it is, setting up the infinite value. So we are setting up the infinite value is there, where you are using that infinite distance. Like we are taking that two comprehensions are there. Like you are taking that comprehension, list comprehension 1 and list comprehension 2. See, here also two loops are involved. So here it is infinite setting also n square. And overall complexity, we can consider it is n square, because it's the highest complexity is considered whenever you have the algorithm. And of course, using less comprehension is having less than n square, but it takes n square is that ideal case. What do you say that, So this is what the Dijkstra's algorithm. And remember, it is a greedy approach. Once you finish that A to C, even you have another way, which is the shortest way. We have already visited one and visited one. From here, A we are choosing means we don't choose from B. So we choose from A only. So that what do you say that, it's a greedy approach. Dijkstra's is using that greedy approach only. Once it will choose that one alternative, it doesn't choose that other alternatives from other vertices. Because right now, you are binded for the A only. So that's it about the Dijkstra's. So I hope it's clear
Why
about
this greedy approach?
Yeah, greedy approach is very simple. Once you entered into one path of it, okay, you believe that all the remaining paths from the current vertices only. Even you have another vertex is there, which is disjoint to A, but this path reaching to D is very shorter than this. Like, you might reach it that B to C, here C is available. So here what happens, the weight is 2 and 3. Reaching from A to D, here it is 7. So you already reach to A. We don't see that other adjacent vertices is there, not adjacent actually. Other route is there, which is the shortest one. We don't find it. We always follow the current path only. Even other paths is there, not it is checking. But other algorithms is there, upcoming algorithms like Prim's and Kruskal's algorithms. What it is, it is updating the versions. Like first version, they don't depend on. They see the other versions also. But here it is, once you fix that A, we don't check the other paths, because always we fix for single source, it is single source. We don't choose that other sources. Clear? Even other sources you find it is the shortest one. That's called greedy strategy, to identify the vertices to visit. Clear? Because it's a single source, always we bind for the source only. Okay. Hello? Hello? Yeah, am I audible? Am I audible?
You are.
Yeah. So it is a single source one. It is a binded for the single source. Once you have been next vertex to visit is based on the shortest distance computed so far. Fine. So again, it does not go back to that. Again, it does not change that whatever source. Already we begin with 0. It fixed that 0 is fixed. Even you find that other shortest path from other vertex from like 3. From 3, you might have other shortest path is there. We don't choose it. We fix it as 0 as a source. That's the reason we call it is a greedy approach. We don't change that source which was already started. Okay. Shall we go for the next? Hello? Shall I go for 5.3? Hello? Am I audible?
Yes, sir. You're on.
So greedy approach is we fix the single source, we traverse from the single source only, even we have an optimized one from the earliest ones. Okay. So yeah, 5.3. So this is negative weights are not possible in the earlier Diksha's algorithm, but here it is single source path is there, but negative weights is there. So please wait. Earlier Diksha's doesn't allow you the negative paths, but in this 5.3 we are using Bellman-Ford is there. This algorithm allows you the negative paths also, negative edges. So let me go for it. That's one. It is also single source is there, but negative weights is possible. Where you can find, yeah. Yes, here it is. So again, they are checking the Diksha's algorithm, what exactly Diksha's is. So keep tracking of it. Recall the burning pipeline analogy, same analogy they are taking. So expected burn time is every time it is updated. EBT is that expected burn time. So in brief, they are explaining you. Initially, burned vertex is going to be the false, where that each I is always from 0 to n. Unburned vertex, which is B of k is making as a false. Unburned one, consider as. Now expected burn time for the starting vertex, it is 0. Otherwise, all other vertices, like I is 0 means we are making expected burn time is 0. Remaining all we make it is infinite. So every time we are making that unburned vertices, that is expected burn time of j less than or equal to expected burn time of less than or equal to k for all k which is k belongs to that unburned vertices, then only it is. So whenever you are, so update that the burning time of the j is true, unburned vertices, and which is subtracted. Unburned vertices is the subtracted remaining value. Here it is subtracted. What exactly is happening is subtracted set of the j is subtracted. We update continuously for each j and k such that we are selecting minimum of that expected burn time, okay, in the two sets, and expected burn time of j plus and w of the jk. So the w of the jk is from the j to k, what is the weight involved, what weight is involved. from J to K. From J to K. So existing weight of the J plus from the J to K means K is going to be adjacent from the J. These two sum, they do it. And so whatever the particular expected burn time you want to make it burning, this minimum, out of this, which one is a minimum? This one is a minimum, we burn it. Instead of this one, another route you find it, which is the shortest one. So these cumulative sum, that minimum is selected. So this is what is happening in Diksha's algorithm. Hello? Yeah.
EBT means
Yes, what is it? EBT means expected burn time. B means burn time, expected burn time. UB is unburnt vertex. So once the burnt vertex is true, burnt vertex of J is true, unburnt is remaining, unburnt minus J. So here the subtracted difference is again unburnt, updating the fit. Okay. So here it is again, they explained you that the Diksha's algorithm, in the negative edges in terms of it. So let's we go for the negative weights. So here it is, they are going with, yeah, the same correctness requires that non-negative only, already same thing. So connecting this X to V and Y to V via W also possible. But remember, negative weights are not possible in the Diksha's algorithm. We cannot do it the negative weights solution using Diksha's one. So that's the reason we go for the next approach is, see, because next approach is, yeah, we have similar kind of slides. Yes, it's one. Look at it. So the difficulty with negative weight is we stop updating the burn time once the vertex is burned. So whenever the negative edges is there, like you have that -1, which is 5, 7, and -3 is available. So whenever you start burning from the X, you are trying to burn this V. But if you consider this way, like Y to V also you can do it, because it is this particular 7 you found it is higher value comparatively this 5, we don't burn it. Because of this -3, it is misleading. We don't consider the -3 in Diksha's. So what happens, so 7 minus 3, it's going to be 4 distance. Even it's a shorter distance, it doesn't consider because of the negative edges. So negative edges is not considered. Recall the negative edge weights are allowed, but no negative cycles are allowed. So no negative cycles is not allowed, but negative edges are allowed in the next algorithm of the Bellman-Ford. So please see that next one is the Bellman-Ford. We are extending the negative weights. So what really it is, Bellman-Ford is, so we can move that Bellman-Ford, which is about yeah, it's a complete one. Suppose we have a minimum weight from 0 to K. So 0 to K. So whenever you are trying to move from 0 to K, there are different edges is there. This is edge 1, edge 2, edge 3, all these L-1 length you need to traverse. So need not be the minimum number of edges. Here length is not considered. Remember, length is not considered. Only the weight is considered. Only the weight is considered. The W1 plus W2 plus W3, that is considered, but it doesn't consider that L-1. Remember that one is. So every prefix of this path itself, you look at here, this is a weight is available here, that is W1. Some number is there. Here W1 plus W2 is there because the total weight is there. Here you have the sum of the W1 plus W2 plus W3 and keep going. So all this one. So once we discover that we discover that L-1, next update we'll fix the shortest path. So what do you know? You continuously update it. It does not mean that we fix it is like 0 to J1 is one path and J1 to J2. We directly move from 0 to W3 where you have a shorter distance might be there. That's what we are trying. So repeatedly, we update the shortest distance. So each vertex based on the shortest distance, if all of its neighbors. So we consider that from the all of its neighbors, we try to figure out that which is the shortest one. So update cannot push this distance. Actual distance is there. After L updates is there. Every time we keep on updating. We keep on updating how much distance is from W1. After updating W2, what is the value? After updating W3, what is the value? In this, all of this, minimum path weight is selected with n number of -1 edges. After n-1 updates, all shortest paths are stabilized. For example, you have seven particular edges is there. So after all updates, like it is 7 vertices is there. After 7 - 1 vertices updates, your values are stabilized. So that stabilization you can see in the next slides, which you can find it, a tabular format is given. You can find here it is. Here you can find it. Yes. Here it is the Belmont Ford. Yeah, it is a complete implementation. Yes, this is a complete implementation. Look at here, it's a complete implementation. So initially, whatever that single source you want to start it, that minimum distance is considered as whenever the vertex is going to be the 0th one. So it's considered as 0, and otherwise all other vertices it's going to be set it that expected burn time is that infinite. So for each vertex 0 to n-1, each edge of j to k, that is number of edges, we are selecting the minimum, and here the distance is updated. It's worked for directed and undirected graph also. Please remember here it is every time the updating is done. So the infinite value is done with infinite value, and we are setting infinite values to the distance. First vertex is setting for the 0. Here remember the values we are fixing is the outer loop is there, which is repeating the number of rows, and inner loop 1 is outer loop 1, inner loop 1, and another inner loop is there, inner loop 2. So if that is this particular vertex is already visited, this vertex is already visited, then what happens, distance we are calculating. So whether the minimum distance of the current one or distance from u and u to v, both of the sum which is going to be the shortest one. So what you do here, it is updating is done. The distance is every time it is updating. Distance is updated. So once the distance is updated, keep on that, like 3 times the nested loops are done. So whenever it is done, see, look at here. One example is given, like yeah, here you can find it. Yes, there is initially, yeah, there is a graph is given. Remember, Belmont Ford allows you that negative weights also. Negative cycles are not there, negative weights are there. You can check it, no negative cycles are there, because it is -4, 2, and then it is, yeah, it is -2, going from -4, and then it is no cycle. Here no cycle is involved. And going from -2 and 1, it is 1, -1, and then it is +2, and +2 is, here cycle is there but no negative cycle. In this case cycle is there but no negative cycle. Negative edges are there, negative cycles. Belmont Ford doesn't work for negative cycles. Negative cycles not allowed. not
Sir,
allowed.
what do you mean by the negative cycle? It means that sum will be the minus.
Yes, some will result the minus.
Okay.
So you are started from the 5 and keeping coming from the 5 only, but it's not resulting the negative. So here that 6 you started, but again you cannot come to 6, like -4, and then it is 2, -2 is there, but it's not forming negative cycle. Again from the 5 you are not going back to 6 because it's a directed one. Clear?
Sir, is it because if it will make a negative cycle, then it will subsequently will be decreasing and decreasing, so it
Yes,
can't.
decreasing and decreasing. Bellman 4 doesn't work.
Correct.
If cycle, due to the cycle, keep on updating that every cycle you are increasing the negative values. The negative values increasing, the cost is not improving. That's the reason negative cycles are not allowed. Negative edges are allowed. But whenever zigzags is there, negative edges is not allowed. Clear?
Got it. Yeah. Thank you.
See, look at now we from this one, different versions are there. Please remember here V means the versions. One particular version, they don't depend on it. The particular vertices is updated every time in a column wise. You keep on looking of this. If you look at this first one, initialize that d of 0 is 0. Keep on increasing that. The particular, whenever the vertices is keep on increasing, you can look at the next one, next column when it is increasing. So from the 0 to 1, the weight is there 10. It is updated. It's fine, no problem. From the 0 to 7, we have a path 8. It's updated, no issues. In this, it's very clear. No problem in this. Okay. Now we go for the next slide, 27. So when you look at this 27, we already got that the values for 0, the values for 1, the value for 8. Clear? So then after it, please see this here. From the 7, we are trying to find out 0 to, we are single source, no? From the 0. From the 0, we are trying to find out that other path, which is 5 is there. See, 0 to 8, sorry, 0 to 7 is 8, and 9 is there. From this, you have that -1, 8 is updated. So 0 to, wait. So you have one path over 6 is not considered, no, right now, because 6 is not yet visited right now. From the 0, we are trying to do that. Already visited one is this. Already visited one is 1. Already visited one is 7. Fine, that's okay. Up to here, this is okay, fine. So we got it 7 and 1 and 0. And after this, from this path, we have to check it. From this, we cannot go for 6 right now. Yeah, 6 we can go. 0 to 8 and this 6, so that 9 is updated. So no problem. So then after it, 0
From
to
1, 5 is updated.
yeah, 0 to 1, it's 10 and 12. 12 is updated to the 5, no problem. So then after it, 0 to, yeah, it's earlier it is updated. These two are recent updated one, no problem. But whenever you see that next one, there might be a change in the values. Please see this one here. Look at here. Earlier, 0 to 5 is 12. Now it is 8. You can find the difference. Did you find it? Earlier, 0 to 5 is 12. Yet this time, 0 to 5 is 8. Did you find the difference then? Did you find it? Hello? Did you find it? So why it is, another version is updated. Another vertex has been updated. So earlier it was 0 is visited. Then 7 is visited. Up to here, no, already it's done. Then 1 is visited. And after that, 6 is visited. Then after it, 5 is visited earlier. Clear? So then after it, what happened, we are trying to update other values. So in this one, they are trying to traverse for 2. They are trying to traverse for 2. So you look at 0 to 2, that is 0, 1 is there, and 10 and 12, 0 to 2. It is 10. Okay, this part is 11 is there. This path is 11 is there. Now we have an optimized path is there. 0 to 8 and 9. 9 and this is 8. And from the 8, wait. How much we got the 10? We have to find out it, no? Yes, it is. Now it is changes down.
It is 5 to 2, sir.
Wait. 0 to
1 and then 5.
0 to 10, it's 12 and minus. Yes, it is. It's right. Something like this. You need to find out it. So from here you can find a way. So that 10 is updated. That's not issue then. But what happened? This 12, it became 8, identified. Earlier it was 12. Now it is 8. Why it is? How it is happened? The version changed. In this, there is a change of this 12 value to 8. How it is happened? The 8 value? 0 to 5. Did you notice this one? Did you notice? Hello? How this 5 you got
Yeah.
it? Yeah, how did you get it?
6 to 1.
Yes.
Like 0, 7, 6.
Yes. 0, 7. Tell me, 0 to 7, it's 8.
7,
And
8.
9
Minus
after
4.
it. 9 after that.
Upwards, sir. 9 minus 4.
Yes.
1.
Here, 9 after it, minus 4. What
We
happened?
got
5. 5.
5.
5,
Yeah.
5 after it.
Again, so it's got 1, right? That's it, sir, for 1.
No, 0 to 5, no, I'm asking. So this 12 became 8.
0 to 5. Oh, okay.
0 to 5,
then
I'm
1
asking.
to. Okay.
0 to 5, how
Then
you got
1
the 8?
Like going to 1, sir. Again, from there, 2 is coming.
This is 8 and 9. 9 after it. After this,
So 6 to 5 directly.
6 to 5 you go it. But what is the distance, What is the distance? Please check it. 9 and then minus 1 is 8. That's the reason. Already we have got the value of 6. That's the reason we got this updated value is 8. Earlier it was 12. So every time you are updating the new values for the columns. So that every time you have updates. See, for each JK that belongs to edge will be updated. Every time you get updated one. For every time you get a minimum. So it does not mean that current weight is updated and stayed back. So once you got a new edge is updated here, we try to update all the values. Even that earlier values also updated. That is what happening in the Belmont folder. So similar way is happening for all. See, for each vertex, for each edge J to K that belongs to the edge, we are getting the minimum and the jth one and weight of the J is updated for every time we update it. So once that every time you update it, see 8 will become, now it is 7. So keep on moving to that other versions. You get that the last one, final iteration, your values are stabilized. See, after here at this place, your values are stabilized. So at this place, your final values are stabilized with all of the how many cycles? Yeah. So if there is a negative cycles also, that discontinue, the distance will be continued. The stabilization is done. Yeah. check the update. Yeah, up to here. So it reduces that any particular distance of V. Every time it will update. If update is done, it will reduce. So finally, the updater final stabilized version is this. So every time a new vertex is added, simple conclusion is a new vertex is added. Whenever a new vertex is added, it will update all previous widgeted distances also. So what happens, every time you will get a new values. Like once a new vertex is found, again we try to traverse from 0. So you will find any optimized way, any updates has been done so far. Due to this new vertex is added, this distance may be reduced via this one or via this one. So that is what called the Bellman-Ford is doing. So this is the complete things about the Bellman-Ford. If you go for the complexity, it's definitely n cube. Sorry, it was a mistaken. It is not n square. It is n cube. So why it is n cube? It's very simple. So n number of times you are repeating, and again m number of times. So of course same n only, because same rows, no. So after that number of columns is taken. So that's it's wrong. It is n cube times. Actually, it is a mistake in the printing of it. Yeah, outer loop number of times it will run.
Infinity is n square.
Yes. Infinity is n square. That is absolutely every time you do it.
Yeah,
because infinity calculation we are setting. Calculation is okay, but we are setting that all number of rows is initially infinite. So it is n times only. It is repeating. Initialization part.
Yeah, so it is talking about initialization part only. No?
Initialization part only.
Yeah. The overall is n3. That is.
Overall is n cube. Yeah, or sorry, here it is overall is n cube.
Yeah, that's what I was saying.
Okay. Sorry. So overall is n cube. So this is what actually this is the Bellman-Ford. So when you shift it for that, same complexity is going on. Yeah, if you shift that one is to the adjacency list. Adjacency list, if you shift it, running complexity is not reduced. The time running complexity is same. No change in it. But space can be reduced. Why it is space can be reduced is, see that adjacency list is there. Adjacency list. We try to do that shifting for it. Overall complexity scanning of and updating is space can be reduced. Here it is each updating is reducing infinite to shifting to the adjacency list. Yeah, it is. I think adjacency list they have to tell that m into n. So adjacency list also same, but only thing is updating is reducing. Why? Because here it is n is required. But what about this one is adjacency list is having a single row. That single row traversing is easy. That means complexity is reduced. So whenever you are using adjacency list, it is m into n. It's m into n. Of course, it is somewhat reduced comparatively n cube. This is what the Bellman-Ford. Yeah. So both are going to be the Dijkstra's and Bellman-Ford. Both are going to be the single source only. But the difference is Dijkstra's one. Sorry. Yeah. But the problem is.
So running time complexity is n cube only.
N cube for matrix. No. WT matrix. Adjacency matrix. But adjacency list is used means it is somewhat reduced. So overall is m into n. Shifting of the elements is reduced.
Like in the adjacency list, should be m plus n.
No. M into n. O of mn. Mn means it's multiplication. It's not m plus n. M into n. Here, no symbol is given means it's m into n only, not m plus n. So Diksha's and Balman-Ford difference is, so it doesn't work for negative edges. Negative edges not allowed. So whenever negative edges not allowed means negative cycles are not possible. Here negative edges allowed. Negative edges allowed. But negative cycles not allowed. Negative cycles not allowed. Not allowed. And when do you see that Diksha's one? It is a greedy approach. It's a greedy approach. Greedy approach of single source only. But it is also single source. Greedy approach with updated versions. So always it is also single source and it is also single source. But the difference is that it doesn't depend on that only one kind of instance. Keep on updating that whatever weights are updated, the cumulative weights. So based on it, the Balman-Ford is. So that's what the difference when you compare with Dijkstra's algorithm and Balman-Ford is. So this is 5.3. Shall I go for 5.4? Shall I go for 5.4? Shall I? Oh yeah. Just give me 1 minute time. I'll come up with it. Yeah. So up to here, it's a single source is done. Now it is all pairs. So first let us we consider it is some of the problem. What really all paths is? All pair paths. Single source is always we start with one origin. We fix that one origin only. That origin we bind for it and we do that finding of the shortest path. So whenever all pairs is there, we are finding that shortest path from every vertex of I to Z. Every vertex. Every vertex. So let me have that we have started from A, B, C, and D. So you can start from something like you have a graph. You can start from A, you can start from B, you can start from D. So whenever single source is there from the A, we are trying to find out the shortest path from to reach that any of the other vertices. But here what happens, from the B we are considering means we don't consider the weight distance between A to B. From the B, what are the different shortest paths are there? Either C is shortest or D is shortest. So that what is the shortest path is your multiple pairs, all pairs. We try to find out all pairs shortest one. All pairs shortest, if you are finding it, some advantage is there. There is a real-time problem. So you can find it. Yeah. See, the one solution they said, run the Dijkstra's and Balman-Ford for each vertex. Consider that 0 as a origin and run it. Consider that 1 as a origin and run it. Consider the 2 as a origin and run it. So then you will get it. The complete solution, we can do that. Like all pairs, we can do it by using run the Dijkstra's or Bellman Ford for each vertex as a horizon. Like 0th one as a horizon, 1 as a horizon, and 2 as a horizon. After like 5 vertices is there, 5 times you run at 5 different horizons, you might get one solution that is all pair shortest path. So that is what actually even you can do with earlier using earlier algorithms. But here it is not like that. We are trying to find out it. Is there any way, instead of using same algorithm and considering that multiple horizons and run the same algorithm on multiple horizons, is there any way? So we have a way for that. Yes, we have a similar kind of slides is that we are going for that. Whichever, yeah. Here it is a unique one, which is all are combined. See, look at here. We have a matrix multiplication. So a square is equal to, if there is a path with length of 2. So what really 2 represents, to reach from I to Z, we required that 2 edges has to be passed. That's what it is meaning of that. A square of that I Z equal to 1 means there is a path between I and Z, but you need to traverse with a length of 2. So for that sum, like, K is there. So A of K, Ik, you reach that Ik equal to Kj equal to 1. That means first you need to reach that I to K. So I to K and then K to Z, because already we have a K. So then we have a path. So in general, we say that one. So in generally, what do you say that is A of that L plus 1 is nothing but A of L multiplying with this A. And if there is a path L plus 1 to that, the sum A is then. So keep on adding to reach that. To reach that, keep on adding. Here there is an alternative approach is given, which you can understand better. So B of K Ij means that you need to traverse K number of it. So if there is a path to I and J, you need to traverse 0 to 1, 1 to 2, 2 to 3, and keep on going K number of vertices you need to traverse to reach from I to Z. Constraint applies to that intermediate one, like B naught of that I and J equal to 1. There is a direct edge is available whenever you have a direct edge. So K plus 1, there is a path. So you have already a direct from that I. And then we use it 0, 1 to the going from that I to K and then K to Z. Like I to K means already said, no. I to K we are going and then K to Z we are going. That is alternate approach they are showing. So how that transitively they are closer, how really they. So in this one, there is a Warshall's approach has been given. You can look at the Warshall's approach. So these are all same slides. Yeah, the 13th one is ended. Yes. Yeah. So Warshall's approach is given. See, look at here. The algorithm on the left also computes the transitive closure. So the Warshall's algorithm. So B of n, which is Ij equal to 1. There is a some path is there by traversing n number of intermediately vertices. In the middle, you need to traverse n number of vertices to reach from I to Z. So where the Bn is nothing but that A plus. So we adopt that Warshall's algorithm to compute all pairs shortest path. All pairs means each pair, like I to J, J to K, K to M, something like that. Every pair we are considering it. And every pair we are finding out the shortest path, the direct edges only, and no intermediary edges is there. So in that way we are considering. So, and in that case, we are considering that Floyd Warshall, where actually Warshall's algorithm, which has been used that method, and they have implemented the other Floyd, so that it's called Floyd Warshall's is. Let me go for that, a complete version of the Floyd Warshalls. I hope that this is a duplicate one. Yeah, 16th one is a unique one. So see here, it is adding up is done for the algorithm to compute that. So if you could look at this one line, SP of that k plus 1, Ij is the minimum weight. SP of Kj, shortest path using that 0 to k minus 1. How do you say that it is the shortest path? SP means shortest path. How do you say it is shortest path? Is by adding all vertices edges. Vertices are linked. Vertices from 0 to k minus 1. This is what they said. So SP to the power of k of Ij is nothing but shortest path using from 0 to k number of vertices. So here SP of Ik is nothing but SP of k of Kij. So I to k there is a path, and then k to j we have a path. Combine the shortest path, we get it I to k and k to j. So there are intermediary vertices is there, but they are connected. They are connected in terms of that I to k and k to j. So the length of the shortest path of overall I to j is intermediate. All vertices length is calculated. But here length is not considered. We are considering the weight only. So weight only considered. So please look at here. Different versions is taken. Same like which have been done earlier. See, look at. Initially, all of them we are setting it to the infinite. Then in the first one, we are trying to update all of the vertices because it is a multi-source one. 0 to 1, 10 is updated. And 0 to 2, which is updated with the shortest one. 0 to 2. Wait. Sorry. 0 to 2. Wait. It's in some matrices there. SP0 direct edges. What exactly direct edges is? From the 0 we don't have any path. From the 0 to 1 it is 10. From the 0 to 8 we have 8. Okay, that's okay, fine, no problem. From the 1 to 2 we have direct one. 2, okay, no problem. This is okay. It is a direct one. From the 2 to 1, 2 is there. 2 to 1, there is a 1. Okay. These are they are all directed. Direct weights was given. No problem in this. It's a direct weights. It's not issue then. So after doing the direct weights, second version was done, which is same. No incoming changes is done. SP1 is same. Whatever the same thing is there. But whenever you come to that SP2, yeah, SP2 there is a change. SP2 there is a change is done. So what the change is done is, earlier it was that 0 to 5 is infinite. So now that 0 to 5 is updated with 12. You can identify the red color values. And earlier 2 to 5 is that 2. 2 to 5 is that infinite is there. Now 2 to 5 is updated with 3 because it is different origin, because you are taking that all pairs. These are all pairs. Here it is all pairs are there. All pairs is there. So you can look at 0 to 7 here, 0 to 7 here. All pairs we are trying to calculate. And similar way, 6 to 5. Earlier we have 6 to 5 is -1. Now it is updated with -2. So which is a better value. What do you say that, And if you go for SP2 to SP1 and then SP2, okay. If you go for SP3, yeah, SP3 there is a change. See, look at here, it is SP3, there is a change again. So 5 to 1, earlier it was infinite, now it is -1. And 5 to 3 earlier it is infinite, now it is -1. See, whatever red color one is updated in each cycle, each version, shortest path is updated whenever next version is done. So keep on doing that 7 vertices, we get it that 8th one. See, 8th cycle is all of the complete values, we got it. This is what the complete values. So all source vertices, which is the shortest paths, is this one. So we got it, the last one values is. So this is the shortest version. So the implementation is this 20. Implementation is this one. Wait, complete implementation is available in 29. Yes, in 29 it was there. They have considered it is adjacency matrix only. So you have infinite setting, and then shape they are considering, that is NumPy array, and we have n square complexity because outer loop and inner loop setting there. This one is n square, and then every time the version is updated. See, look at here, version is updated. So the adjacency matrix version is updated. After setting the version values of the first horizon, then we are using outer loop and inner one and inner two, where you are considering that updated values with the minimum. And last column values only we are returning. We are returning the last column values, which is the last column value, which is here it is. We don't need that all other things, only the last column values. This is what the last column values, which is completely updated. The complete updated values are considered. So we return that last column values only. This is what the complete implementation. Yeah, this is pretty much. Yeah. So it is a single nested loop. The space is the space can be reduced, but overall complexity is n cube. No way of reducing, but space can be limited because the slices are changing. Like SP slice is overwriting the previous SP dash, so that the slices is updating keep on, so that space can be reduced to n square, but running time of the complexity is n cube only. So it works with negative edge weights, assuming that no negative cycles. Negative cycles are not there, but negative edges are there. This is what exactly the Freud watches. Okay. So I hope that it's pretty much then 5.4. Is it okay then? By this, we have ended with multiple source path. Multiple source path is ended. Multi-source mode. Okay then. Shall we go for the next one? Shall we proceed? Okay. Yeah.
Sir, in the previous question, why we have taken like 5 is the last column, sir? 5.
Wait. Yeah. This one. This one, no? It's completely filled one. The shortest path is completely filled, which is all vertices has been done with it. All vertices has been done with it. That's
like in the code where in the code, sir.
Yeah, in the code it is taken only the column value. See, I can show you that execution. If you could look at this one is Floyd versus WT. I have the version of the code. I can show you. Yeah, Floyd versus. See, look at here. They are returning the columns, you know.
Yeah.
Only the column values we are getting the result.
Okay.
The column values. Okay then. So every time the column values only we are returning. Clear?
Okay, sir.
The column values only, because instead of returning all complex in matrix, like you are getting all versions, you know, but I want only the latest one. That is all columns you are getting. So this columns only. First column, second column, and third column. Okay then. So how many number of columns are there? Only that one.
Okay, sir. Done.
Yeah, by this one, the graphs are ended. So then we have that spanning trees. See that spanning tree is a tree. It can be considered as a graph, but it's not a cyclic graph. That's what's simple. A tree can be considered as a graph, but it is a cyclic one. That's what a simple truth about the trees. Anyway, we'll see about the trees in the next coming lectures, but it is pretty much, it is showing that how really it is. See, look at here. Earlier, whenever you think about that spanning trees, in that they are talking about what is really spanning tree. So there is a real-time scenario was given. We have that all connected graph is there, like a fully connected districts, a fully connected different districts are there, like A to B and C and D. So what happened, due to the cyclone, so we have been lost that connection. So what really they want to do is, the government wants to make it. First, there should be a road point. So once road point has been restored, so we can provide that other facilities, maybe food and daily needs, whatever they wanted. To making of this particular minimum road, so they try to connect it. What possible ways they try to connect is, so very simple, A to B and then B to D and then A to C is one way. Again, you need not connect A to D. So because if you go for B, you can reach the D. If you go for A, you can reach C. Otherwise, they can do that C, D, and then they can be connected to B. From here, they can connect it to A. So what exactly, what set of roads should be restored? Only 3 set of roads is more enough. 3 set of roads is enough, which can connect that all 4 districts or four places which have been cyclomatic disorder has been happening. So there is a cyclone has happened. Similar way, there is an internet service provider is there, which they are connecting. Different lines have been connected to the different locations. So there is a secured redundancy is required. If any time this complete connections, like one to many connections is there. If any connection we lose it, there is other additional connection which is a standby. Like if you have been additional standby other than this actual connection, we have a secondary cable. This secondary cable is a minimized line. It's a minimized one. Actual line, if it has gone, you can use the secondary line. So if you want to reach the C, you can reach that A to B, but B to C, something like that. So there is a way that's called, spanning tree. What do you call, it connects that all of them. So remember, spanning tree is always minimum set of edges. Remember it, minimum set of edges that has to be done. So if you could look at the minimum set of edges, so let's we go for, still this example is continued. Yeah. Yes, this place is perfect. Look at here, we have fully connected graph is there, 0, 1, 2, 3, 4. So what I do is, I want to build a minimum set of edges so that graph remains connected. So recall the minimum tree is that adding an edge, the tree creates a loop, removing the edge and disconnects the graph. So if you have been, see, look at this one, 3 and 1 and 2 and 4. See, adding an edge, it definitely creates a loop. See, if I'll add it one particular edge here, definitely loop is created. No loop should be there in the spanning tree, minimally connected. So if we are adding an edge, definitely it creates a loop. Similar way, so let's you remove this one. This is a spanning tree. If you remove any of the edge, if I'll remove this edge, immediately what happens, two disconnected graphs are created. So this is one graph, another graph is created. So then only we can say it's a spanning tree. If you are adding edge, it is creating a particular tree, is creating a loop, then definitely it's a spanning tree. If you remove edge, definitely it creates a two disconnected. If you remove an edge, it will disconnect it. Two different graphs it is dividing. So definitely it's a spanning tree. So we want to connect that a tree which is connecting all vertices, spanning one, without creating any kind of cycles. That's what they'll tell about the next slide. So please look at the next slide is the spanning trees. So you can see the spanning trees, the next one. Wait. Yeah. Spanning trees, the next possible slide is 7 is done. Then they are going with spanning tree with cos. So please look at the cos. Same slide is keep going. Yes. See, look at here, it is ended. Yeah, this is ended. See, look at here. One particular spanning tree is not okay, but we are having multiple spannings. See, this particular tree, you can construct it 0, 3, 4, 1, and 2. This is one way also it's possible. And you have another way is there. 0, 1, 2, 3, and 4 also possible. This is also possible because you are connecting that all of the vertices with minimum number of edges. That's okay. But thing is, we are associated with edge with cost. Please look at here. Edge with cost is there. Cost. Adding a cost of all edges in the tree among the different spanning trees, choose the minimum one. Choose the minimum one. So if you choose the minimum one, so you can have a look. So we have a particular one is 114, you can return it, and you have a cost of 44 also. So please look at where it is 114, 0 to 3, and then 3 to yeah 3 to 6 we can go. Then sorry, 3 to 6 it's not, 3 to 1, I'm sorry, because you have to mention that vertices, no. 0 to 3, 3 to 1 not possible, 3 to 1 is okay. Yeah, 3 to 1, then 1 to 2, then 2 to 4. Let me see what is the weight. 0 to 3 is 18, and this is 24, 24, and 24 to 44, and 44 to 4, which is 44 and 8, it is 52.
52.
Yeah, this is one spanning tree. Another spanning tree is there, 114 also. So you can have 114, something like this. There is one more spanning tree, which is not minimum one. Of course, we traced one of the minimum. But out of all these, minimum one is this 0 to 1, and 1 to 3, and 1 to, sorry, I'm sorry. Yes, yes, exactly. Perfect, perfect. Because it's not a sequence. No? 0 to 1 is there. Yes. 0 to 1 is there. And then we have 1 to 2 is there. Another edge. And then 0 to 3 is there. Sorry, 1 to 3 is there. And then we have one more edges. 2 to 4. 2 to 4. So here 0 to 1 is weight is 10. plus, and then 1 to 2 is 20, then 1 to 3 is 6, then we have 2 to 4 is 8, which is that 30, that's 44, which is going to be least one. So we choose the least one, least cost is considered. So that's the advantage of it. When the spanning trees is there with weights are there, we try to find out the minimum cost of that edges. That edges only we connect, other edges we avoid it. So that's the minimum cost required to construct that particular spanning trees. So that is what exactly is. And then if you go for, yeah, some of the facts. So please look at factors, first fact and second factors. Fact number 1, a tree has that n number of vertices, exactly n minus 1 vertices, also edges only it's there. Please look at that earlier diagram. Spanning tree, remember it's not a graph, spanning tree. 1, 2, 3, 4, 5. 5 vertices is there. We have the 4 edges only. 1, 2, 3, 4, which are green color, which is n minus 1. That's the fact number 1. Please look at the fact number 1. Initially, one particular one particular vertex is considered as one component, and then deleting ij will split it. Like if you delete one edge means definitely it split it into 2 components because they are tightly connected, you know. If any of the edge you remove it, definitely it separates that into 2 different components. 2 different components means 2 different trees, 2 different graphs. So otherwise there will be a still path to J and D, then you combine a cycle. Even you disconnect, still the particular graph is there means definitely there is a cycle. So each edge deletion creates one more component. Like A to B and B to C is there. It's not, the cycle is not there. If you remove one edge, like this edge is removed, then what happened? B has one tree, A and C has another tree. So 2 different component it's going to be. So deleting n minus 1 edges means definitely n components. Like this is complete tree is there. If you do that n minus 1 edge, that means this is removed and this is removed, means totally we have 3 components. N components are remaining. So n minus 1 edges, if you remove it, all of the vertices are going to be isolated and they are individual. That is about the fact number 1. And fact number 2 is adding an edge to the tree must create a cycle. So if this is not having cycle, this is not having cycle, this is a tree, let's say consider as a spanning tree. If you add any of the additional edge, immediately it creates a cycle. So that is, then it is going to be a spanning tree. A tree is connected if there is already path from I and J. If new edge is added, I to Z, combining with this path, so it forms cycle. So B to C, if there have path, but indirect path is there, no worries. Another direct path, if you are establishing, definitely it creates a cycle. So adding of it, definitely it creates a problem. So now you look at that another fact is there. Another fact is there. So what's another fact is, in each tree pair, the pair is there which is connected with a unique path. Remember, they are unique path. See, there is a path is there this way. There is a path is there this way. So this is not a tree. It's going to be a graph because it's a cycle is happened. Because of 2 paths is there. If only one path is there, let us consider this is not there. This is not there. So when this is not, okay, this is not there. Only simple, this one is disconnected. We have only reachability is from I to J is only this path. We don't have a reachability because we are removed one of the edge. One of the edge, if you remove it, cycle is removed. One cycle is removed, only you have only one unique path. One unique path is available. If more than one path is available, then definitely it's not a spanning tree. It's a graph. We can say it's a cyclic graph. So this is about that. And let me go for that 16. Yeah. See, there is an observation. So very simple observation. a graph is connected, a graph is cyclic means definitely n minus 1 edges. What they want to tell you is, if any of the two following facts is done, then third one is implied. Third one is implied. If graph is connected, graph is acyclic, then definitely n minus 1 edges is there. So definitely n minus 1. For example, an acyclic graph is there, n minus edges is there, definitely it's a connected graph. So that is, if two of them is there, third one is there. If graph is connected, so graph is having n minus 1 edges means definitely it's a acyclic one. So this is what exactly, if two facts are true, definitely third fact is connected. So that is what one observation they done it. So this is about that. And if you keep going, the building of a spanning tree, all these are duplicating one. So which is animated one. Yeah, here it is. Here it is. There are the two natural strategies is there. So how to build a minimum cost spanning, because already I said there is a total cost of spanning tree. We got 52 and we got 44 and we got 114 also, one example, but we did not find it. So in our trace, so out of it 44 is the minimum. How to pick out that a minimum cost spanning tree, MCST. So that is done through Prim's algorithm and Krishkal. So the Prim's algorithm is start with the smallest stage and keep growing it. This is the approach they are using in Prim's. But when the Krishkal, what they are doing is, there is a ascending order of weights, ascending order of edges. Initially they sort it. So that sorted one, that particular sorted edges, they are trying to connect them. Like first smallest one, next one, and keep on going to the higher level. The edges are combined one. So that is called Krishkal. So this is the what the difference is, Prim's and Krishkal. And this is all about spanning trees. Next coming two PPTs are going to be the Krishkal and Prim's. First Prim's is there, then the Krishkal is there. So is it okay? Did you understand that minimum spanning? What really minimum spanning is? Once a graph is disconnected and no cycle is formed, definitely it's a spanning tree. In the spanning tree, we are trying to build a spanning tree with total weights of least. That's called minimum spanning. That's called MCST. Is it clear, MCST? Minimum cost of spanning tree?
Yes.
Okay. So shall I go for the next then? I'm going for the next, huh? So there are two strategies is there. Prim's is there, Krishkal is there. So we are going for the Prim's first. So Prim strategy is, see the duplicate things is there. We try to avoid it, animated one. Yeah, it's very simple strategy then. Yeah, here it is showing. Yes, it's in the growing stage. It's going. Already I said, every time you are picking up that the edge which is with the smallest weight. See, look at a graph is having vertices and edges, where W is nothing but connected one between that two vertices. G is assume is connected. See, all of these are connected. Graph is called as a connected graph, which all of them are having weights. Okay, so V number of vertices is there, E number of edges is there. So finding the minimum spanning tree. So now we are using the first strategy number 1, incrementally growing the minimum cost of the spanning tree. Start with the smallest weight edge. Out of all these, the smallest edge they are choosing. The smallest one is 1 to 3 because its weight is that 6. They don't choose that vertex. They choose that smallest edge in terms of weight. Remember, weight. So once weight is there, definitely 2 vertices are participated. 1 and 3 vertices are participated. The weight is 6. So they don't choose that single source, they don't choose multiple source. One particular edge which is having smallest weight is chosen. After that, they try to extend 1 to 0. So 1 to 0 they are trying to choose, because 1 to 2 is there, 1 to 0 is there. Next smallest one is this, so that 10. Weight 10. This edge is selected. After that, we cannot add 0 to 3, because 0 to 3 is forming cycle. It is forming a cycle. So cycles are not allowed. Spanning tree means it is not a cyclic graph. So it is not cyclic one. Yeah. So it's not cyclic. So we don't choose this one. So then after it, so we don't choose this. Yes. We don't choose this one, 0 to 3. So instead of it, we are trying to extend 1 to 2. 1 to 2, it is extended means 20. So that it's a 20 is extended. So then after it, extend it 2 to 4. So we are not extending 3 to 4 because it's a 70. We are trying to extend 2 to 4. It's 8. So it is totally, we are getting it as 44. So it is a minimum Scott spanning tree, MCST. So this is what the prims is. So what really happening in the prims? They have been shown in the simple kind of numbers. So we go with the detailed one, which is, yeah, all these are combined. Yes. Sorry, here it is. Yeah. Please look at here. What really is happening? Total vertices is there. Total edges is there. So 3 edges is, which is already added to MCST. 3 vertices is there, which is already added to MCST. Edges is added, vertices is added. Initially, so 3 vertices and 3 edges are going to be 0. They are empty. That we consider it is empty. Empty, we can say that. Empty list or empty dictionary, we can say that. So choose the minimum weight IJ, set it to the TV. Initially, they choose that minimum weight. The minimum weight means it contains the source and destination, I and J. So it is added. And then the weight of that is going to be added. So the edge is added, 1 and 3. And the vertex is going to be added. So that particular vertex is added. Vertices. 1 is finished, 3 is finished. Of course, this weight is there. This weight is internally, it is representing its weight. Next one, repeat the same one. Same one, 1 and 0. So 1 is already added, only 0 is added. Next 1 and 2, 1 is already there, 2 is added. Next 2 and 4, 2 is already added, 4 is added. Okay. So T is nothing but the total edges and 3 edges, and V is nothing but the total vertices which are there. And it is not forming cycle. Hello. Let me mute all. It's not forming cycle. It's not forming cycle. And when it's forming cycle, that particular edge is going to be avoided, just like 0 to 3 is avoided. Because already 0 is already there. 3 is already it's there. So that cycle it is forming. Repeating cycles are not allowed. And if we keep going of this one. Yeah, it is minimum separator lemma they are using. How really it is connecting using minimum separator lemma. They're all repeated one. Yeah, here it is. Same one. Assign each. Yes. Here it is. Yeah. Up to here it's right. See, look at what really is that. So let's V be partitioned into, V is the total number of vertices. They are partitioned into 2 things. So U and W, 2 different sets. 2 different sets is. Let's edge is connected between 2 vertices. Like this is edge connected between U and W. U is a part of the capital U, W is a part of it. because it contains a set of vertices. It contains set of vertices, which is a purple color and red color. So whatever you are connected U to W is going to be the minimum one. You might have a other path. You might have other path, something indirectly. You might have other path between U dash to W, but we don't consider it because it is more weight than this minimum. So every MCST must include the E, where the E is nothing but minimum cost edge. Then only we are. So you might have multiple paths are there between connecting of these sets. Between U to W, you might have some other route is there, but we don't consider it. We consider the minimum one only. That minimum only added to that MCST. That's called minimum cost spanning tree. So now assume that each edge is a Unix index. See, look at, sometimes what happens, same weights are maintained. Like U to W, you have a edge which is the same weight, and another path is there. U to W1. It is also having some kind of weight. So this is weight 1, weight 2. Both of them are having same weight value, 10 and 10. Then what happens, a unique index value 0 to m-1 is added. So every particular vertex is being added with the index position, first come first serve basis, which is having a smaller index. That vertex is selected. W and W1, W is selected comparatively W1 because it could be a W0. 0 will come first, comparatively 1, so that we select this edge only, even you are having same weight in the next edge. Clear? So that's what we define. EI is less than Fj. So that is, if you consider weight of E is less than weight of J, or equal weights is there and comparatively index is I less than J. Whenever equal weights is there, definitely I will come prior to the J. So that's what the I less than, because index positions are assigned whenever same weights are available. So this is about the correctness of this one, PRIMS 1. We can call that minimum separator of lava. Minimum separator in the sense the complete graph edges are going to be, vertices are divided into two sets, which is U and Ws. And then we keep going. Same thing is repeated. Yeah, 30 we have seen, no? This is 30. Same thing we are repeating. Yes, 38 is the last one. Not the last, actually. It is sequence for the last. Yes, the next one is implementation. Yeah. Look at, already we said. So in Prim's algorithm, so that three vertices is W is nothing but V minus TV, which is, three vertices. Total vertices, from the total vertices, subtracted one, which is W. So algorithm picks the smallest connected total vertices, three vertices, and weights whatever three vertices are connected, and they are having the smallest connectivity of weight, which is called that MCST. See, all vertices are connected. It doesn't miss that any of the vertex. All vertices are connected and with minimum weights. So in fact, that V belongs to that capital V, which is combination set of vertices. So way that V is nothing but a subtracted value of it every time partition we are getting. The smallest edge is leaving must belongs to that, which is leaving, the smallest weighted it's leaving any vertex must belongs to. If you are leaving that actual set of vertices, it belongs to the MCST. When it is leaving, so actual vertices set is leaving means it is added to MCST. Getting out from the capital V and adding into MCST. So here we started with overall minimum cost edge. Instead, you can start with any vertex. Already I said we don't start definitely always from 0 horizon or 1 horizon or 7 horizon. We always choose that any vertex which is smallest one. So first iteration we'll pick up the minimum cost vertex. So keep implementing this, Prims with the list. See, they are choosing that prims with adjacency list. Using adjacency matrix also we can do, but better complexity we don't get it. That's what directly they did with adjacency list. So if you go the implementation, the complete implementation, which is done in the 42. So adjacency list is better than the adjacency matrix. That's what the reason they chosen directly adjacency list only instead of using adjacency matrix. So initially they have done it that adjacency infinite value as usual. Then it is getting that infinity they are setting, and widgeted of 0 is true. And remember here they are trying to pick out that minimum one. See, look at here. So the minimum one, add the vertex 0 to tree, directly they added vertex 0. Here they are finding out the distance when it is less than the minimum distance. So what is the minimum distance is here, already it is done. The minimum distance is infinite value. So first distance, what you are finding, definitely it is going to be that less than the minimum, and it is not widgeted, and widgeted of u. So then we are updating whatever it is. If no vertices is there, then we are breaking it. That is the last ultimate condition. And the tree edges is nothing but here MCST. Whatever edge is removed from the tree vertices, that's going to be added to that MCST. MCST is nothing but here tree edges. So after adding that each particular MCST, we are selecting the distance which is a minimum only, the minimum of that from the distance of this V vertex to D. Which particular vertex is having the minimum one, that minimum one is selected for the distance. So this is what they keep on updating. Finally, tree edges is. So for this complexities, if you think about this one is N, and inside loop is there, and another inner loop is there, but it is not nested. For loop with keys is there, for loop with keys is there, which is another inner loop. It does not belongs to inner loop of U, it belongs to the inner loop of I. So if you could see the complexity of it, so each iteration how much it's taking, and overall complexity is Mn only, which could be n cube sometimes it may not be that n cube. So overall is m into n. The reason is simple. So we are having that loops is not nested one. Here it is going to be m and n number of times it is updating, so that definitely it is O of mn. So can we do the better? Yes, we can do the better, but the better is that nearest neighbor they are finding in this way. See, look at this moment, they are trying to find out directly with nearest without using another nested loop. They avoided. See, they directly do that minimum without doing another nested loop. So earlier it's done with the, see, earlier it done with the another nested loops is there, but here directly they are finding the minimum. It's a better one without using another two nested loops is. So improved implementation. So whenever improved implementation is there, the complexity is very much reduced. So which is that n square. Simple one is n square. So it is adjacency list they have used, but whenever you are using adjacency matrix, it takes much time. Not better than n square. Definitely it's poor than n square. So definitely it reaches to n cube. So this is what the premise is. And critical strategy is same, but what they do is they do earlier sorting. If you go for critical, yeah, critical is same to that one, but here before starting of that one, they start the sorting and then start it. You go for the critical. Yeah, tell me someone, Ravikant, who wants to tell something. Hello. Shall I proceed then? Yeah, sure. Definitely, I'll wind up it because only just I'll introduce that crystal and then I'll close it. No worries. Just quickly I'll introduce. See, crystal is, yeah, it is directly. I'm going that where the crystal vital part is there, where it is explained. That slide gives you that more details. Yeah, here is the part. Yeah, here is the part. Strategy number 2. Remember, all of the edges are here ascending order. They sorted before start of the minimum cost spanning tree. All of the edges are sorted. Once they sorted, then only they do it. See, first once they sorted, always ascending order is there. The starting smallest one is 1, 3. Next added smallest one is 2 and 4. Next smallest one is 0 and 1. But we cannot add 0 and 3 because it is forming a cycle. We don't add it. 18 is not going to be added. So first 1 and 3, then 2 and 4, then 0 and 1. Next smallest one is 1 and 2. So here include that edge if it does not create that cycle, then only we are including. Like we are not including 0 and 3. That's what happening. See, if you go for directly implementation, you can understand the strategy. Very quickly you can understand. Just I'll go for the directly implementation. So that implementation will tell you what really it is quickly then. Yeah, here it is. Yes, here it is. Please see that here. So we have a doing of sorting of the edges. Before you start that traversing of the particular minimum cost spanning tree, we are building it. We try to sort it. So what you do is sorting is, first we have that already WList keys are there. We try to create the edges as a components. Each of them is a one component. One component is nothing but it contains that all of the edges with respective weights is there. So these components are there. Each of the component, it contains that all of the edges with weights and as well as source and destination. And all of them are sorted. For the sorting purpose, what they did is weight as a first element. They have taken the first one is weight and then after it. So that it will sort based on it because 3 things is there. D and U and V is there. They try to change it. So in terms of it, so that weight is going to be the first one. For that only the loop, this loop is for changing that first component as a weight. Then they sort based on the weight. Once they sorted it, we have a loop. So this component U is not checking that no cycle is formed. This is checking no cycle is formed. No cycle formed. Whenever no cycle is formed, we try to append that particular one. You need not compare minimum and this because already they are in ascending order. Simply you can append it. After appending it, we try to get the component. Then we are updating the component W with latest one of C. And then again component W with component V. So this is equal weights are there. See, whenever equal weights are there, equal weights, then what do you do that we are choosing index value. That's what index value status. Whenever equal components are there, then we are choosing that index value. So this is what is happening. So, and this is pretty much, and when you compare the complexity, overall complexity is n square only, which is crystallus. Partitioning is somewhat this one. Yeah, it is. You can reduce it, but somewhat you need to write that separate procedure for find, separate procedure for union. If you maintain a separate data structure for finding a vertex and union of it, then you can reduce the complexity of the critical algorithm. So this is, yeah, this is pretty much then. Yeah, that's it. That's it from my side. Please let me know that any clarifications further, or shall we wind up the session then? Because it's too late. Yeah. So thank you. Good night all. Bye-bye then.